There is something unusual about where we are. Not just our planet, not just our solar system, but our entire corner of the cosmos. The Milky Way, along with thousands of neighboring galaxies, rests inside an enormous hollow in space, a region where matter grows thin and galaxies become scarce. This hollow stretches nearly 2 billion light-years across. Astronomers call it the KBC void, named for the researchers who first measured its true extent. We are not observing this void from outside, looking in through telescopes at some distant curiosity. We live within it. Our measurements, our observations, everything we see when we look out at the universe, all of it is shaped by our position inside this cosmic emptiness. Tonight, we will explore what this means. We will trace how astronomers discovered we live somewhere unusual, what effects this has on our understanding of the universe, and why some scientists believe this void might be breaking our most fundamental theories about how the cosmos works. We will move through this carefully, gently, giving each idea the time it deserves. Before we begin, if you find value in these explorations, a quiet like or subscribe would mean more to me than you might imagine. It helps these stories find others who appreciate taking time to understand the universe's deeper patterns. Your presence here matters. Let us start with a simple question that leads somewhere profound. What is a void, and why should we care that we live in one? To understand why the KBC void is so disturbing, we must first understand what voids are and why they exist at all. The universe is not uniformly filled with galaxies. Matter clusters into vast structures, the cosmic web we observe today, leaving enormous empty regions behind. These empty regions are voids, and they are not rare. They occupy most of the universe's volume. A typical void might span 50 to 100 million light-years across. Inside, galaxy density drops to a fraction of the cosmic average, perhaps 10 or 20% of normal. These voids are not completely empty. Galaxies exist within them, but they are sparse, scattered, isolated. An observer inside a typical void would see far fewer galaxies than we do, the night sky noticeably darker, more empty, more lonely. Voids form through a process that begins with the universe's earliest moments. After cosmic inflation ended and the universe entered its more gradual expansion phase, quantum fluctuations that had been stretched to cosmic scales became frozen into the fabric of space-time. These fluctuations represented tiny variations in energy density, regions where matter would eventually be slightly more or less concentrated than average. The cosmic microwave background that ancient light released when the universe was 380,000 years old preserves a snapshot of these variations. When we map this radiation across the entire sky, we see temperature differences of only a few parts in 100,000. Hot spots correspond to slightly denser regions. Cool spots mark slightly less dense regions. These patterns are not random noise, but organized structure reflecting physical processes in the primordial plasma. What transforms these barely perceptible ripples into the dramatic cosmic architecture we observe today? The answer lies in gravity's relentless amplification. Consider a region that begins only 1% less dense than its surroundings. Initially, this difference is negligible, but gravity pulls matter preferentially toward denser regions. As material flows away from our underdense region toward its denser neighbors, the density contrast grows. What was 1% becomes 2%, then 5%, then 20%. The process accelerates because lower density means weaker gravity, means matter flows out even faster. Meanwhile, the regions receiving this inflowing matter grow denser still. They're strengthening gravity, pulling in material from ever wider areas. The cosmic web emerges from this process with matter streaming from what will become voids toward what will become filaments and clusters. It is like watching a river network form through erosion, with water carving valleys and leaving ridges between. Here, gravity carves voids and leaves filaments of matter between them. The mathematics describing this gravitational instability was first developed in the 1930s and 40s by physicists studying how small perturbations grow in self-gravitating systems. They showed that in an expanding universe, density contrasts grow at a rate determined by the expansion rate and the matter density. Given the observed properties of our universe, we can calculate how quickly structure should form, how large voids can grow in the time since the Big Bang. Computer simulations starting from observed initial conditions naturally produce cosmic webs with filaments, clusters, and voids. The simulations match observations beautifully, reproducing the statistical properties of structure we observe across vast cosmic volumes. This agreement between theory and observation is one of modern cosmology's great successes, evidence that we understand the basic physics of structure formation. Yet theory imposes constraints. Structure grows at a finite rate determined by gravity's strength and the universe's expansion. In 13.8 billion years, density contrasts can amplify by factors of thousands or tens of thousands, but not arbitrarily. The initial fluctuation amplitude, measured precisely in the cosmic microwave background, sets a baseline. From this baseline, we can calculate how large structures should be today. For voids specifically, the calculation involves tracking how underdense regions expand relative to the cosmic average. Early in cosmic history, when the universe was matter-dominated and expansion was decelerating, voids could grow efficiently as matter streamed toward denser surroundings. But as dark energy began dominating about 5 billion years ago, accelerated expansion changed the dynamics. Structure formation slowed dramatically. Voids largely stopped growing. Their current sizes reflect how far they expanded before dark energy froze further evolution. These calculations predict maximum void sizes around 150 to 200 million light-years in radius at present day, depending on assumptions about cosmological parameters and void definition thresholds. Voids significantly larger than this require either initial conditions we have not observed, physics we do not understand, or simply represent rare statistical fluctuations in the tail of the probability distribution. This brings us to the uncomfortable observation. The KBC void extends roughly 1 billion light-years in radius, possibly more depending on how boundaries are defined. 10 times the theoretical comfort zone. Not impossible perhaps, but improbable enough to warrant scrutiny. But wait, how do we even know the void exists? How do we measure something defined by absence rather than presence? This is not a trivial question. Finding something is easier than finding nothing. A galaxy shines with the light of billions of stars. We can photograph it, measure its spectrum, determine its properties. But a void is characterized by what is not there, by galaxies that should exist but do not. How do we map emptiness? The answer requires patience and enormous amounts of data. Mapping voids requires measuring distances to thousands or millions of galaxies. Photographs show galaxies scattered across the sky, bright points against the darkness, beautiful spiral shapes and elliptical glows spread across our view. But photographs alone cannot reveal three-dimensional structure. They show us a projection, a flattening of three-dimensional reality onto a two-dimensional image. We see where galaxies appear on the sky, but not how far away they are. We need depth information, distances, to construct a three-dimensional map showing where matter actually is distributed through space. Astronomers measure distances using redshift, one of the most powerful tools in modern cosmology. When galaxies move away from us, their light is stretched by cosmic expansion. This stretching shifts the light toward longer wavelengths, toward the red end of the spectrum, an effect we call redshift. The amount of redshift tells us how fast a galaxy is receding. In an expanding universe, recession velocity relates to distance through the Hubble law, named after Edwin Hubble, who first discovered the universe's expansion in the 1920s. Measure redshift, calculate velocity, infer distance. This relationship works remarkably well on average across large scales. If we measure redshifts for millions of galaxies and use the Hubble law to convert those redshifts to distances, we can map out the three-dimensional distribution of galaxies through space. This is exactly what large galaxy surveys do, and the results are spectacular, revealing the cosmic web in stunning detail. But the process has complications we must understand. Galaxies do not move only with cosmic expansion. They also have peculiar velocities, local motions caused by gravity from nearby structures. Think of it this way. The universe's expansion carries all galaxies apart like raisins in rising bread dough. But superimposed on this general expansion, galaxies have their own local movements, like swimmers moving through water while the water itself flows downstream. A galaxy falling toward a massive cluster moves partly from expansion and partly from gravitational attraction. Its observed redshift combines both effects, the expansion velocity and the peculiar velocity. This makes distance measurements tricky because we cannot easily separate these two contributions. When we measure a galaxy's redshift, we see the total effect, and disentangling how much comes from expansion versus local motion requires additional information or assumptions. For distant galaxies, billions of light-years away, this complication is minor. Peculiar velocities are typically a few hundred kilometers per second. Expansion velocities at large distances are tens of thousands of kilometers per second or more. The peculiar velocity becomes a small correction, a few percent effect that barely changes the distance estimate. But for nearby galaxies, within a few hundred million light-years, peculiar velocities can be substantial, hundreds of kilometers per second, enough to significantly affect distance estimates. A galaxy with a peculiar velocity toward us appears closer than it actually is. A galaxy with peculiar velocity away appears more distant. These systematic errors can obscure structure if we are not careful. Despite these complications, large galaxy surveys map structure successfully. Teams of astronomers spend years, sometimes decades, pointing telescopes at millions of galaxies, measuring each one's spectrum, determining its redshift, building catalogs containing positions and distances for vast numbers of objects. The Sloan Digital Sky Survey, one of the most ambitious projects in astronomical history, has measured redshifts for millions of galaxies over more than 2 decades of observations. The 2-degree field survey, conducted with a telescope in Australia, mapped hundreds of thousands of galaxies across the southern sky. Other surveys, both completed and ongoing, add to this growing database. These surveys require enormous effort. Measuring a single galaxy's spectrum takes minutes. Measuring 1 million galaxies takes thousands of hours of telescope time, often stretched over years of observations. The data must be carefully calibrated, analyzed, checked for errors. Bad measurements must be identified and removed. Systematic errors must be understood and corrected. The work is painstaking, unglamorous, essential. The result of all this effort is 3-dimensional maps of cosmic structure spanning billions of light years, revealing the universe's architecture in unprecedented detail. These maps show the cosmic web. They show filaments, clusters, walls, and voids. They show structure at every scale, from individual galaxies to superclusters spanning hundreds of millions of light years. And they show something troubling about our local cosmic neighborhood. In the early 2000s, astronomers analyzing galaxy distributions noticed something odd about our local cosmic neighborhood. Galaxy densities seemed lower than average out to substantial distances. Not just a local underdensity, not just a nearby small void, but a large-scale deficit extending hundreds of millions of light years in all directions. Initial estimates were uncertain. Defining void boundaries is subjective. How empty does a region need to be to count as a void? 20% of average density, 10%. Different thresholds give different answers. And measuring average density itself is challenging, since we have only one universe to sample. But as surveys improved and techniques refined, the evidence strengthened. Our local region, out to distances of roughly 1 billion light-years, contains fewer galaxies than the cosmic average. The deficit is not dramatic, perhaps 20 to 30% below average, but it is persistent and statistically significant. We live in an underdense region. In 2013, astronomers Ryan Keenan, Amy Barger, and Lennox Cowie published a comprehensive analysis. They used multiple galaxy catalogs and careful statistical methods to characterize the void's properties. They found a region roughly 700 million light-years in radius, about 1.4 billion light-years across, where galaxy density drops significantly below cosmic average. They called it the KBC void, named after their initials. Subsequent studies refined the estimates. The void may be even larger, approaching 2 billion light-years in some directions. Its boundaries are not sharp edges, but gradual transitions from underdense interior to denser surrounding structures. The void is not perfectly spherical, but somewhat elongated, and importantly, it is not completely empty. Galaxies exist within it, including our own Milky Way, but they are sparse compared to typical cosmic neighborhoods. How empty is empty? In the densest parts of the cosmic web, in rich galaxy clusters, there might be hundreds or thousands of galaxies within a few million light-years. In typical regions along filaments or walls, dozens of galaxies might occupy the same volume. In the KBC void's interior, that same volume might contain only a handful of galaxies. The difference is stark. If you could teleport from the Milky Way to a galaxy in the Virgo cluster, roughly 50 million light-years away in a denser region, your night sky would transform. Instead of the scattered galaxies we observe through telescopes, you would see galaxies everywhere, bright, naked-eye objects filling the sky like stars do for us. The difference between living in a void and living in a cluster is the difference between rural emptiness and urban density. But here is the disturbing part. The KBC void's existence alone is strange but perhaps explainable as a rare statistical fluctuation. The universe is vast. Rare events happen somewhere. Maybe we just happen to live in an unusual place. Except the void does more than just exist. It appears to be affecting our measurements of the universe itself, and this is where the crisis begins. One of cosmology's most important numbers is the Hubble constant, quantifying how rapidly space expands. This single parameter determines cosmic age, distance scales, and the universe's ultimate fate. For decades, astronomers have pursued ever more precise measurements using independent techniques. The expectation was that different methods would converge on a single value as measurements improved. They have not converged. Instead, the discrepancy has grown more statistically significant as precision increased. One approach uses the cosmic microwave background, analyzing temperature fluctuations to extract cosmological parameters, including expansion rate. This method yields a value in the mid to low 60s when expressed in kilometers per second per megaparsec. Another approach uses distance ladder techniques, calibrating distances to nearby supernovae and extending outward to measure expansion directly. This local method produces values in the low 70s, about 10% higher. This disagreement is called the Hubble tension, and it has resisted resolution despite years of intensive scrutiny. Both measurement teams have checked and rechecked their work. Both use well-understood physics. Both have refined their techniques, reducing uncertainties, yet the discrepancy persists at high statistical significance. Something is wrong, either with one or both measurements, or with our understanding of what they should measure. Various explanations have been proposed. Perhaps early universe physics differs subtly from our models in ways affecting cosmic microwave background interpretation. Perhaps supernova calibrations harbor unrecognized systematics. Perhaps new physics operates at energy scales or distance scales we have not fully explored. Each proposal faces challenges, either failing to explain the full discrepancy or contradicting other well-established observations. The KBC void offers a different perspective on this problem. Local expansion measurements sample our cosmic neighborhood, perhaps out to distances of 1 or 2 billion light-years depending on the specific technique. If this neighborhood is systematically underdense, expansion here proceeds faster than the cosmic average because less gravitating matter means weaker deceleration. We would measure a biased value higher than the true cosmic mean. Meanwhile, cosmic microwave background measurements average over the entire observable universe, sampling scales vastly larger than any local structure. They yield the genuine cosmic average, unbiased by our particular location. Both measurements would be technically correct but measuring different things, one local and biased, the other global and representative. This is where the KBC void enters as a potential resolution, or at least a partial one. If we account for our location inside a large underdensity, local expansion measurements might be biased upward compared to the cosmic average. The void provides a conventional explanation using known physics, requiring no modifications to general relativity or dark energy properties, no dramatic revision of cosmological theory. It suggests the measurements are both correct, but sampling different things. Understanding whether the void explains the Hubble tension requires more than observation. It requires computation, sophisticated computer simulations that model how structure forms and evolves. Let us take time to explore this because simulations have become indispensable tools in modern cosmology. Creating a cosmological simulation starts with initial conditions representing the universe shortly after the Big Bang. These conditions include the density fluctuations created during inflation and observed in the cosmic microwave background. The simulation volume might span hundreds of millions or even billions of light years, containing billions of particles representing both dark matter and gas. The simulation then evolves forward in time, calculating how these particles move under gravity's influence. Each particle feels gravitational forces from all other particles. Computing these forces is challenging. In principle, it requires calculating forces between every pair of particles, a computational task that grows as the number of particles squared. For billions of particles, direct calculation would be impossibly slow, requiring centuries even on the fastest supercomputers. Instead, simulations use clever algorithms that group distant particles together and calculate collective forces. One common approach is the tree algorithm, dividing the simulation volume into cubic cells that are recursively subdivided into smaller cells, creating a hierarchical tree structure. When calculating forces on a particle, distant groups can be treated as single massive objects if they are sufficiently far away and closely clustered. This reduces computation time dramatically, making billion-particle simulations possible. As the simulation proceeds, structure emerges naturally from the initial conditions. We watch the cosmic web take shape. Over-dense regions attract more matter and grow denser. Underdense regions lose matter and become voids. The patterns appear without being explicitly programmed. They are emergent phenomena, arising inevitably from gravity acting on the initial density field. The largest simulations run on supercomputers using thousands of processor cores working in parallel. A single simulation might run for weeks or months, consuming millions of CPU hours. The data produced can reach hundreds of terabytes, requiring specialized facilities for storage and analysis. Running such a simulation is like conducting an experiment, but the experiment happens inside a computer rather than a laboratory. We set initial conditions, specify physical laws, and observe what happens. By running many simulations with different random initial conditions, we can build statistical distributions of structure properties. How common are voids of different sizes? How do void properties depend on cosmological parameters? What probability should we assign to finding a void as large as the KBC void? These are questions simulations help answer. The results are intriguing but ambiguous. Simulation studies reach different conclusions depending on volume, resolution, and statistical methods. Some find that structures approaching the KBC void scale should appear perhaps once per observable universe volume, making our location near such a structure unlikely but not absurdly so. Others calculate much lower probabilities, suggesting the void represents an extreme outlier that challenges standard cosmological predictions. This spread in conclusions reflects both technical limitations and genuine scientific uncertainty. Large volume simulations capture broad statistical properties but sacrifice resolution, potentially missing subtle features affecting rare structure probabilities. High-resolution simulations see detailed physics clearly but cover limited volumes where extreme events may not occur within the simulation box. Different groups make different trade-offs, leading to different probability estimates. Moreover, these calculations tackle the extreme tail of structure distributions where statistical methods become most uncertain. Linear perturbation theory breaks down for large density contrasts. Non-linear evolution introduces complex dependencies difficult to characterize analytically. Numerical approximations may not capture all relevant physics. Each limitation introduces systematic uncertainties that bracket probability estimates over ranges spanning orders of magnitude. As computational resources grow, simulations improve, covering larger volumes at higher resolution for longer evolutionary times. Each advance refines probability estimates, though consensus remains elusive. The KBC void sits uncomfortably at the boundary between rare but allowed and genuinely problematic, precisely where our ability to calculate probabilities is weakest and where interpretation becomes most contentious. But does the void actually explain the Hubble tension? The answer is complicated. Simple calculations suggest the void should affect local expansion by a few percent, roughly the amount needed to explain the tension. This is promising. But detailed calculations depend on void properties, its exact size, its density profile, its shape. Different assumptions give different results. Some studies find the void can explain most or all of the tension. Others find it contributes, but does not fully resolve the discrepancy. Part of the problem is that we do not know the void's properties precisely. Is it 700 million light-years in radius or closer to 1 billion? Is galaxy density 30% below average or only 20? These details matter for calculating expansion effects. Another complication is that peculiar velocities, local gravitational motions, also affect measurements. Disentangling expansion effects from gravitational flows is challenging. Galaxies falling toward overdense regions outside the void create patterns of motion that mimic or obscure void effects. Multiple research teams have published studies with conflicting conclusions. Some argue the void fully explains the Hubble tension. Others argue it contributes, but something else must be involved. Still others suggest the void is not large or empty enough to have significant effect. The debate continues. But even if the void does not fully explain the Hubble tension, its mere existence poses questions. Why are we here? Is it coincidence that we find ourselves inside one of the universe's largest voids? Or is there something deeper at work? This brings us to one of cosmology's most controversial ideas: observer selection bias. The notion that our location in the universe is not random, but somehow influenced by the requirements for observers to exist. In its weakest form, this is trivially true. We must exist in a location where life is possible. We cannot find ourselves in the intergalactic void between galaxy clusters, in the core of a star, or in the early universe before stars formed. Our existence requires planets, which requires stars, which requires galaxies, which requires structure formation. We necessarily live in a universe and location where these conditions are met. But the KBC void raises a stronger question. Does living in a large underdense region somehow make observers more likely? Could voids be preferential locations for life? At first, this seems backwards. Voids contain fewer galaxies, fewer stars, presumably fewer planets. Fewer planets means fewer chances for life. Surely observers should more likely exist in dense regions with many galaxies. But consider stellar evolution and heavy element production. Stars forge heavy elements, carbon, oxygen, nitrogen, iron, elements essential for planets and life. These elements are created in stellar cores and distributed through space in supernova explosions. Multiple generations of stars are needed to build up substantial heavy element abundances. In dense environments like galaxy clusters, star formation happens rapidly and early. Many stars form, burn through their fuel, and explode, enriching the environment quickly. But these same environments are violent. Supernovae are frequent. Galaxy collisions are common. Tidal interactions strip gas from galaxies, quenching star formation. The environment becomes hostile to planet formation and stability. In voids, evolution proceeds more slowly but perhaps more gently. Galaxies are isolated, undisturbed by neighbors. Star formation proceeds gradually over longer timescales. There are fewer supernovae per unit volume, less radiation, less violence. Planets that form may be less likely to be sterilized by nearby cosmic catastrophes. This is speculative, to be clear. We have no evidence that void environments are better for life. We have no evidence observer selection bias operates at all beyond the trivial requirement that we exist where life is possible. But the KBC void's existence raises the question: if we live in one of the universe's largest voids by pure chance, that is a remarkable coincidence. The void's size places it in the extreme tail of the probability distribution for structure sizes. Most of the universe's volume exists in more typical regions. Finding ourselves in such an unusual location is surprising. But if living in voids somehow makes observers more likely, perhaps through gentler environments or other mechanisms we have not considered, then finding ourselves here is not surprising at all. It is expected. We are more likely to exist in locations where life is easier, even if those locations are unusual by cosmic standards. This is profoundly uncomfortable reasoning. It smells of anthropic arguments, the idea that the universe's properties are explained by the requirement that we exist to observe them. Most physicists recoil from such arguments. We want to understand the universe through fundamental laws, not through contingent facts about observers. Yet anthropic reasoning has had successes. The cosmological constant problem, the question of why dark energy's density is so small, has no known solution from fundamental physics. Some physicists argue the only explanation is anthropic. If dark energy were much larger, structure could not form and observers could not exist. We necessarily find ourselves in a universe with small dark energy because only such universes contain observers to ask the question. The KBC void may be similar. Perhaps voids this large are rare but not impossible. Perhaps we happen to live in one because such locations are favorable for observers. Or perhaps it is pure coincidence and we are reading too much into it. The truth is, we do not know. And this uncertainty is precisely what makes the KBC void so fascinating and troubling. Let us step back from speculation and examine what we actually know about the void's structure. It is not a perfect sphere of emptiness, but a complex three-dimensional structure with varying density across its volume. The void is roughly centered on our position, with the Milky Way located somewhere in the interior, perhaps not at the exact center, but well within the underdense region. Density increases gradually as you move outward from the interior toward the boundaries. There is no sharp edge where the void ends, but rather a transition zone hundreds of millions of light-years thick, where density gradually rises to cosmic average. The void is somewhat elongated, slightly longer in some directions than others. This asymmetry may reflect the initial density fluctuations from which the void formed, or it may result from gravitational interactions with surrounding structures. Voids are dynamic objects, evolving as matter continues flowing from their interiors toward denser regions at their boundaries. Within the void, structure still exists. The local group, containing the Milky Way, Andromeda, and dozens of smaller galaxies, is here. The Virgo cluster, about 50 to 60 million light-years away, sits near the void's edge, or just outside it, depending on exactly how you define boundaries. Scattered throughout the void's volume are other isolated galaxies and small groups, less densely packed than in typical regions, but present nonetheless. Mapping the void's density profile requires measuring distances to thousands of galaxies in all directions. This is challenging and ongoing. Different studies using different galaxy catalogs and different methods produce slightly different maps. But the overall picture is consistent. We sit in a large, underdense region extending hundreds of millions of light-years in all directions. One question is whether the void is a single connected structure or multiple underdense regions that happen to align along our line of sight. Answering this requires three-dimensional mapping, not just measuring distances, but determining the full three-dimensional positions of galaxies. This is difficult because peculiar velocities distort redshift-based distance estimates. Current evidence suggests the void is a real three-dimensional structure, not a projection effect. But confirming this requires better data. Future galaxy surveys will measure redshifts for millions of additional galaxies, refining our maps and reducing uncertainties. Another question is how the void compares to other voids. Are there other voids this large elsewhere in the universe? Or is the KBC void truly unique? Finding other large voids is challenging because we can only observe them from the outside. From Earth, we look out in all directions, seeing galaxies at various distances. If we see fewer galaxies in a particular direction at a particular distance, that suggests a void. But precisely characterizing distant voids is difficult. We cannot measure their density profiles as accurately as we can for the KBC void, where we have detailed local measurements. Some surveys have identified other large voids at various distances. These voids have sizes ranging from a few 100 million to perhaps 1 billion light-years across. None appear quite as large as the KBC void, but uncertainties make direct comparisons difficult. It is possible other voids of similar size exist, but have not been fully characterized. What we can say is that voids the size of the KBC void are rare. Surveys covering large volumes find many smaller voids, but few approaching 2 billion light-years. This rarity is part of what makes the void's existence troubling. Rare is not impossible, but rare requires explanation. In standard cosmology, structure sizes are constrained by the amplitude of initial density fluctuations and the time available for growth. The cosmic microwave background shows us initial fluctuations were small, about 1 part in 100,000. Gravity has been amplifying these fluctuations for 13.8 billion years. Given these constraints, structures larger than a certain size should be extremely rare. Calculating precise probabilities for structures like the KBC void challenges both our computational abilities and our statistical methodology. Different studies arrive at estimates ranging from mildly surprising to extraordinarily improbable, spanning several orders of magnitude. This variation reflects not just technical differences but fundamental questions about how to assess likelihood when working with a single cosmic realization. Consider the conceptual challenge. Should we ask, what probability governs finding any void this large anywhere in the observable universe? This calculation must account for available volume and the number of possible locations. Rare per location becomes likely somewhere given sufficient space. Or should we ask specifically about our location within such a structure? This involves not just existence, but positioning, a different and typically lower probability. These are not merely technical distinctions, but reflect deep questions about how to apply probability theory to cosmology. We observe one universe from one location. Unlike laboratory experiments, where we can repeat measurements many times to build statistics, cosmology offers no such luxury. Every probability statement rests on assumptions about ensemble averages, about what constitutes a fair sample, about whether our position is randomly drawn from some distribution. These assumptions are philosophically subtle and potentially unstable. Let us consider what alternatives exist if we take the void seriously as a problem for cosmology. One possibility is that our cosmological model is wrong or incomplete. Perhaps gravity does not work exactly as general relativity predicts on the largest scales. Perhaps dark energy is not uniform but varies across space. Perhaps dark matter has properties we have not accounted for. Any of these would affect structure formation and potentially allow larger structures than standard models predict. Modified gravity theories, alternatives to general relativity, have been proposed for various reasons, including explaining dark energy without invoking a cosmological constant. Some of these theories predict different structure formation histories. Perhaps in such theories, voids can grow larger in the time available. But modified gravity faces challenges. General relativity is extraordinarily successful at explaining observations from solar system scales to cosmological scales. Any modification must preserve relativity's successes while only changing predictions where needed. This is difficult. Most modified gravity theories either fail to match observations or reduce to general relativity in relevant regimes. Varying dark energy density is another option. If dark energy was stronger in some regions and weaker in others, structure formation would proceed differently in different places. Perhaps the void formed in a region where dark energy was relatively weak, allowing more efficient evacuation. As the universe expanded, dark energy could have become more uniform, leaving behind a large void as a relic of earlier spatial variation. This idea faces challenges from observations. The cosmic microwave background shows the universe was extraordinarily uniform at early times. Any significant spatial variation in dark energy would have left imprints in the CMB. We see hints of small variations, but nothing dramatic enough to explain void formation. Another possibility is that initial fluctuations from inflation were not perfectly Gaussian, that is, not following the simplest statistical distributions. Most inflationary models predict Gaussian fluctuations, but non-Gaussian fluctuations are possible in some models. Non-Gaussianity would affect the probability of extreme structures like very large voids. Current CMB observations constrain, but do not completely rule out small amounts of non-Gaussianity. Future observations may detect non-Gaussian signatures or tighten constraints further. If non-Gaussianity exists, it would affect structure formation predictions and potentially make large voids more probable. Or perhaps the void is not as large or empty as current measurements suggest. Perhaps systematic errors in distance measurements or galaxy catalogs have led us to overestimate its size. Perhaps what appears as a single large void is actually several smaller voids aligned along particular directions, creating the illusion of one giant structure. This is possible but becoming less likely as measurements improve. Multiple independent studies using different data and methods consistently find a large underdense region around us. Unless all these studies suffer from the same systematic error, the void appears real. A more radical possibility is that we have misunderstood the cosmological principle, the assumption that the universe is homogeneous and isotropic on large scales. The cosmological principle is a simplifying assumption, not a proven law. It allows us to build tractable models of the universe, but perhaps it is wrong on some scales. If the universe has large-scale structure beyond what standard models allow, if homogeneity only emerges on scales larger than we can currently observe, then the KBC void is not a problem. It is just part of a more complex large-scale structure we have not fully mapped. This possibility is profound. The cosmological principle underlies all modern cosmology. Abandon it, and we must rebuild our models from scratch. Measurements of cosmic expansion, dark energy, even the universe's age all depend on assuming homogeneity. If that assumption fails, everything becomes more complicated and uncertain. Current evidence supports the cosmological principle. Galaxy surveys show the universe becomes increasingly uniform on scales beyond 1 billion light-years. The cosmic microwave background is extraordinarily uniform across the entire sky, consistent with homogeneity and isotropy. These observations would be difficult to explain if the universe had large-scale structures dramatically violating the cosmological principle. But these observations are not definitive. The CMB shows conditions when the universe was 380,000 years old, and structure has grown enormously since then. Perhaps large-scale structure today is more extreme than the CMB suggests. Galaxy surveys are incomplete, biased toward brighter galaxies, and limited by observation time. Perhaps we are missing large-scale patterns not yet fully characterized. The truth is, we do not know whether the cosmological principle holds perfectly, approximately, or not at all on the largest observable scales. The KBC void does not prove the principle fails, but it raises uncomfortable questions about how well we have tested it. There is another possibility we should consider, one that is both mundane and troubling. Perhaps the void exists, is as large as we measure, and is not that improbable after all. Perhaps our probability calculations are wrong, too conservative, underestimating how common large structures actually are. Calculating structure probabilities requires understanding the full distribution of density fluctuations and how they evolve. This distribution is not simple. It is non-Gaussian, even if initial fluctuations were Gaussian, because gravitational evolution is non-linear. Overdense regions collapse faster than linear theory predicts. Voids expand and empty faster. The tails of the distribution, the rare extremes, are difficult to characterize accurately. Most probability estimates come from computer simulations. Run many simulations with different random initial conditions and count how often structures of various sizes appear. This gives statistical distributions. But simulations have limitations. They cover finite volumes, smaller than the observable universe. They use approximations for subgrid physics. They may miss rare configurations that require enormous volumes to appear. Understanding how the KBC void compares to other large voids helps us assess whether it is truly exceptional. The Boötes void, discovered in 1987 and spanning roughly 330 million light-years, was once considered remarkably large. Yet, the KBC void is perhaps 5 to 6 times larger by diameter, over 100 times greater by volume. This difference matters because structure formation theory predicts that larger voids become exponentially rarer, not linearly. A void twice as large might be 100 times less probable. Other substantial voids have been discovered. The giant void in Canes Venatici spans perhaps 1 billion light-years. The Eridanus supervoid, also roughly 1 billion light-years across, may explain a cold spot detected in the cosmic microwave background. Each discovery raises questions about whether our models adequately predict large void abundance. However, comparing voids across different surveys is challenging. Different studies use different definitions for what counts as a void, different density thresholds, different boundary criteria. These choices dramatically affect measured sizes and apparent abundance. Detecting large voids at great distances is also difficult, requiring data quality we often lack. As surveys improve, we may find that large voids are more common than current catalogues suggest, or we may confirm their rarity. The uncertainties remain substantial. Perhaps in reality, voids as large as the KBC void are rare, but not as rare as simulations suggest. Perhaps one such void per observable universe volume is not improbable. Perhaps we simply happen to live near it. This would be unsatisfying because it leaves questions unanswered. Why are we near it? Is our location influenced by observer selection or pure chance? But it would mean the void does not break cosmology, does not require new physics, is simply an unusual but allowed structure. The debate continues. Papers are published arguing various positions. Observers refine measurements, theorists refine calculations. Everyone awaits better data. This is science in progress, messy and uncertain, exactly as it should be when confronting genuinely difficult questions. Let us examine how the KBC void might affect other observations beyond the Hubble tension. One effect is on measurements of large-scale flows, the organized motions of galaxies toward overdense regions. The cosmic web creates a gravitational landscape. Galaxies flow along filaments toward clusters. These flows are called peculiar velocities, deviations from pure cosmic expansion. Measuring peculiar velocities is challenging. The observed redshift of a galaxy contains contributions from both cosmic expansion and peculiar motion. Disentangling these requires independent distance estimates, measurements not based on redshift. Various methods exist, including Tully-Fisher relations for spiral galaxies and fundamental plane relations for elliptical galaxies, but all have significant uncertainties. Despite challenges, large-scale flow measurements have revealed bulk flows, coherent motions of galaxy groups across hundreds of millions of light-years. These flows indicate mass concentrations beyond what we can see directly, including structures hidden behind the Milky Way's disk where dust obscures observations. The KBC void should affect these flows. Galaxies inside the void should be flowing outward, away from the underdense interior toward denser boundaries. Galaxies outside should be flowing away from the void or moving tangentially, avoiding the underdensity. These patterns should be detectable in flow measurements. Some studies find evidence for such patterns. Others find flows that seem inconsistent with a large nearby void. The data are noisy and interpretations vary. Flow measurements are notoriously difficult, and different teams using different methods sometimes reach different conclusions. One particularly interesting observation is the so-called dark flow, a claimed detection of bulk motion in a preferred direction extending out to very large distances. If real, such a flow would be difficult to explain with standard cosmology, potentially indicating structures far beyond the observable universe influencing motions we see. But the dark flow's reality is disputed, with some studies confirming it and others finding no significant detection. The KBC void potentially contributes to or explains some flow anomalies. Outflow from the void could contribute to apparent bulk motions, but whether the void fully explains all flow observations remains unclear. Better measurements are needed. Another potential effect is on the cosmic microwave background. The CMB is extraordinarily uniform, but not perfectly. Beyond the tiny primordial fluctuations, there are secondary effects from structure along the line of sight between us and the CMB. One such effect is the integrated Sachs-Wolf effect. As CMB photons travel through evolving gravitational potentials, they gain or lose energy depending on whether structures are growing or decaying. In a universe with accelerating expansion, potentials decay as dark energy begins dominating. Photons passing through these decaying potentials experience a net blue shift, adding slightly to the CMB temperature in those directions. Large voids should create an inverse effect. As voids expand, their gravitational potential wells become deeper, paradoxically. This is because voids expand faster than the cosmic average due to lower density. Photons falling into deeper potential wells are blue shifted, but when they climb back out, the well has deepened, so they are not red shifted by the same amount. The result is a net blue shift, appearing as a cold spot in the CMB where the photon passed through a supervoid. Multiple groups have searched for such cold spots associated with known voids. Some claim detections, others find null results. The expected signal is small, only a few microkelvin, difficult to detect unambiguously given the CMB's intrinsic fluctuations and observational noise. The KBC void should produce a weak cold spot signal in the CMB averaged over large angles corresponding to the void's size. Detecting this requires careful analysis accounting for the void's three-dimensional structure, our position within it, and the CMB's complex foreground contamination from our galaxy and local structures. Some studies claim tentative detection of such a signal, others find no significant effect. As with many void-related observations, the data are marginal and interpretations differ. Better measurements and better theoretical models of what to expect are needed. One complication is that the KBC void size means it subtends an enormous angle on the sky, potentially tens of degrees depending on exactly how you define its extent. Effects on such large angular scales are challenging to measure because there are only a few independent samples. You cannot average over many voids at different locations to reduce noise. We have only one void seen from one position in one universe. This highlights a general challenge with the KBC void. It is a unique structure, or at least rare. We cannot apply the usual statistical approaches that rely on large samples. Every measurement is marginal. Every detection is tentative. This makes definitive conclusions difficult. Let us explore what future observations might tell us. Several upcoming surveys and missions should significantly improve our understanding of the void and its implications. Several major observational programs currently underway or planned for the coming decade will dramatically improve our understanding. The Dark Energy Spectroscopic Instrument aims to measure 35 million galaxy redshifts over 5 years, providing unprecedented three-dimensional mapping of cosmic structure. The Vera-C Rubin Observatory will repeatedly photograph the southern sky, detecting billions of galaxies and enabling statistical studies of structure formation at scales from individual galaxies to supervoids. The Euclid Space Telescope will observe billions of galaxies to constrain dark energy properties and test whether they vary across space or time, potentially revealing whether spatial inhomogeneities in dark energy contributed to void formation. The Nancy Grace Roman Space Telescope will conduct infrared surveys probing the universe's expansion history with sensitivity surpassing previous missions. Each instrument brings unique capabilities. Together, they will map our cosmic neighborhood more completely than ever before, characterize the void's properties with higher precision, identify comparable structures across the observable universe for statistical comparison, and test predictions from various cosmological models. The data flood from these missions will either confirm current estimates of the void's exceptional nature or reveal that large voids are more common than present catalogs suggest, fundamentally changing how we assess the KBC void's significance. Beyond these specific missions, the general trend in astronomy is toward larger samples, better measurements, and more complete sky coverage. Every improvement helps address questions about the void. Does it exist as currently characterized, or have we overestimated its properties? How does it affect local measurements? How common are similar voids elsewhere? Complementing observations, theoretical work continues. Improved simulations with larger volumes and better resolution help assess structure probabilities more accurately. Analytic models of void formation and evolution provide insights into what affects void sizes. Both approaches refine our understanding of what standard cosmology predicts, making it clearer whether the KBC void is consistent or problematic. One particularly important direction is advancing our observational capabilities. Beyond the major surveys already mentioned, technological innovations in spectroscopy, imaging, and data analysis continue accelerating our ability to map cosmic structure. Multiplexed fiber optic spectrographs can observe hundreds or thousands of galaxy spectra simultaneously, dramatically increasing survey efficiency. Machine learning algorithms can identify faint galaxies and estimate redshifts from photometry with increasing accuracy. Adaptive optics systems correct for atmospheric distortion, sharpening images and revealing structure at smaller scales. Each technological advance opens new windows on the void's properties. Higher spectral resolution reveals gas kinematics within void galaxies, showing how their evolution differs from cluster galaxies. Deeper imaging detects fainter, more distant galaxies, filling gaps in our spatial maps. Better computational modeling couples ever larger simulations with more sophisticated physics, from star formation to black hole feedback, testing whether void environments affect galaxy evolution as theory predicts. The synergy between observation and theory drives progress. Observations reveal unexpected patterns that theories must explain. Theories predict subtle effects that observers must verify. Neither alone suffices. Together, they advance understanding through constant dialogue, each refining the other, gradually converging on robust conclusions that survive multiple independent tests. Another direction is exploring alternative cosmological models. If standard cosmology struggles to explain the void, what modifications might help? Can we identify minimal changes to the standard model that accommodate large voids without contradicting other observations? This is challenging because cosmology is tightly constrained. Any change ripples through multiple predictions, and maintaining agreement with all data while fixing one problem is difficult. But this challenge is also an opportunity. Genuinely new physics often emerges when observations cannot be explained within existing frameworks. The void may be pointing towards such new physics, or it may be a particularly unusual but allowed structure within standard cosmology. Distinguishing these possibilities requires theoretical creativity alongside observational rigor. There is a philosophical dimension to the KBC void worth acknowledging. It confronts us with the question of whether our location in the universe is special or typical, a question with deep historical resonance. For most of human history, we believed Earth was the center of the universe. The Copernican revolution displaced us from that central position, showing Earth orbits the Sun. Subsequent discoveries pushed us further from prominence. The Sun is an ordinary star among billions in the Milky Way. The Milky Way is an ordinary galaxy among billions in the observable universe. We are not central, not special, just one unremarkable location among countless others. This progression toward mediocrity is sometimes called the Copernican principle, the idea that we should not expect to occupy a privileged position. It has been a useful guide. Assuming Earth is typical of planets, the Sun typical of stars, the Milky Way typical of galaxies, has led to successful predictions and understanding. But the KBC void potentially violates this principle. If we live in one of the universe's largest voids, our location is atypical. Most of the universe's volume lies in voids, so in that sense we are not unusual. But most volume lies in smaller voids or in moderately dense regions. Living in such an extreme underdensity places us in the tail of the distribution. Does this matter? Should we expect our location to be typical? Or is the Copernican principle only a guideline, useful but not absolute? The answer may depend on observer selection. If observers are equally likely anywhere in the universe, then finding ourselves in an unusual location is surprising, evidence either of rare chance or potentially of a problem with our models. But if observers preferentially exist in certain locations, then finding ourselves in such a location is expected, not surprising at all. This brings us back to anthropic reasoning, the idea that we must find ourselves in locations compatible with our existence, even if those locations are unusual. In its weak form, this is trivial. We must exist where life is possible. In its strong form, It suggests our existence somehow selects or explains the universe's properties, a notion many find philosophically uncomfortable. The KBC void forces us to confront these questions more directly than most astronomical observations. It is unusual enough to be surprising, but its existence is not obviously impossible or inconsistent with known physics. How we interpret it depends partly on how we think about probability, selection, and our place in the cosmos. Perhaps the most intellectually honest response is uncertainty. We do not know whether the void is improbable enough to worry about. We do not know whether observer selection operates in ways that affect our interpretation. We do not know whether future observations will confirm the void's properties or reveal we have overestimated them. We are confronting the limits of our knowledge, and that is uncomfortable but appropriate. Science does not always provide clean answers. Sometimes it reveals problems we cannot yet solve, questions we cannot yet answer. The KBC void may be such a problem, a puzzle we will live with until observations or theory advances enough to resolve it. Let us consider one more aspect of the void that deserves attention: its dynamics. The void is not a static structure, but evolving as the universe expands. In the early universe, shortly after recombination, when the cosmic microwave background was released, the region that would become the KBC void was slightly underdense, perhaps only 1 or 2% below average density. This subtle underdensity was sufficient. Gravity pulled matter from the underdense region towards surrounding overdensities. As matter left, the density decreased further, strengthening the effect. The void expanded and emptied. But void expansion is not unlimited. As the universe's expansion accelerates due to dark energy, the physics changes. Dark energy prevents further growth of structure. Overdensities cannot collapse more because dark energy's repulsive effect resists gravity. Similarly, voids cannot expand or empty further because surrounding matter is being pulled outward by dark energy rather than falling into the void. Dark energy also affects our local measurements in ways we must account for. Because dark energy drives accelerated expansion, the expansion rate is not constant but increasing with time. Measuring the current expansion rate, the Hubble constant, requires understanding this acceleration. Different models of dark energy predict different acceleration histories and thus different current expansion rates. Uncertainties in dark energy's properties translate to uncertainties in the Hubble constant. Moreover, if dark energy's density varies spatially, even slightly, this would affect structure formation differently in different regions. Perhaps the KBC void formed in a region where dark energy was slightly weaker, allowing more efficient evacuation before dark energy began dominating. As the universe evolved, dark energy could have become more uniform, leaving the void as a relic of earlier spatial variation. This idea faces challenges. The cosmic microwave background shows the early universe was extraordinarily uniform. Any significant spatial variation in dark energy would have left detectable imprints. We see hints of small variations, but nothing dramatic enough to explain large-scale structure like the KBC void. Still, it remains a possibility worth exploring as we refine measurements and models. This means the void's growth is largely finished. It will persist, possibly for the remaining life of the universe, but will not continue expanding dramatically. Its current size represents its approximate final state. This is fortunate for observers like us. If the void were still rapidly expanding and emptying, local conditions might be changing on timescales relevant to civilization. But with structure formation effectively frozen by dark energy, we can expect our local cosmic environment to remain relatively stable. However, individual galaxies within the void continue moving. They have peculiar velocities, local motions that cause them to drift over time. Galaxies can fall out of the void toward denser regions at the boundaries. Others can fall inward from the boundaries. Over hundreds of billions of years, galaxies slowly redistribute, though the void's overall structure persists. Our own Milky Way has peculiar velocity. We are moving at about 600 kilometers per second relative to the cosmic microwave background rest frame. This motion results from gravitational attraction toward overdense regions and repulsion from underdense ones. We are flowing along the gravitational currents of the cosmic web. Part of this motion may be outflow from the KBC void. If we are in an underdense region, we should be moving away from the void center toward denser surroundings. Measurements suggest we are indeed moving roughly toward the Virgo cluster and more distant structures in that direction, consistent with outflow. But disentangling various contributions to our motion is difficult. One question is where exactly within the void we sit. Are we near the center or toward the edge? Different studies give different answers, depending on how you define the void's boundaries and center. Some place us relatively centrally. Others suggest we are displaced toward one side. This uncertainty affects predictions for how the void influences our measurements. Living in a void also affects galaxy evolution in our neighborhood. Galaxies in voids evolve differently than those in denser environments. In galaxy clusters, frequent interactions disturb structure, triggering starbursts or stripping away gas through ram pressure and tidal forces. These violent processes transform galaxies rapidly, often quenching star formation within 1 billion years. Void galaxies evolve more peacefully. Without nearby neighbors, they retain their gas, maintain regular structures, and form stars at steady rates. The result is that void galaxies tend to be smaller, bluer, gas-rich, and actively star-forming, quite different from the massive, red, gas-poor ellipticals common in clusters. Our Milky Way shows characteristics consistent with void evolution. We are a large spiral with active star formation, abundant gas, and few signs of recent major disturbance. Our last major merger occurred 8 to 10 billion years ago. Since then, we have evolved relatively peacefully, forming stars steadily, avoiding the violent major mergers common in denser regions. The void environment may have preserved conditions favorable for life. Star formation in the Milky Way has proceeded gradually over billions of years, enriching our galaxy with heavy elements necessary for planets and complex chemistry. In denser environments, intense starbursts and frequent supernovae might create more hostile conditions, sterilizing large regions or disrupting planetary systems. The void's gentler conditions might allow more stable environments where life can originate and evolve undisturbed. This raises questions about observer selection. If life is more likely in gentle void environments, then observers would disproportionately find themselves in voids, despite voids containing fewer galaxies overall. Our location would be less surprising, explained through selection rather than chance. Testing this is difficult, with only one example of life, but it illustrates how the void connects to deeper questions about our cosmic circumstances. If we are near the void's center, we sample its most underdense region, and local measurements should show maximum deviation from cosmic average. If we are toward the edge, effects should be smaller. Pinning down our precise location within the void requires better three-dimensional mapping of surrounding structure. This mapping is improving but slowly. Each new galaxy survey adds data, refining our picture. But comprehensive mapping requires measuring redshifts for millions of galaxies in all directions, a task requiring dedicated telescope time over many years. Patience is required. Looking toward the far future, what will become of the KBC void over cosmic timescales? As dark energy continues driving accelerated expansion, galaxies beyond certain distances will recede faster than light can travel. They will cross our cosmic horizon, disappearing from view. Galaxies currently within a few billion light-years will remain visible and gravitationally bound to the local group. But galaxies in more distant voids and structures will vanish. The KBC void's boundaries, lying at distances around 1 billion light-years, should remain within our observable horizon for a long time, perhaps tens or hundreds of billions of years. But eventually, if dark energy remains constant or strengthens, even relatively nearby structures will recede beyond observation. In the extreme far future, observers in the local group will see only their immediate neighborhood, a merged Milky Way Andromeda galaxy, and perhaps a few satellite galaxies surrounded by darkness. The void, the cosmic web, the entire large-scale structure beyond our local gravitational domain will be gone, not destroyed, but simply receded beyond the horizon where light can never reach us again. These future observers will have no evidence of the universe's expansion, no cosmic microwave background, no distant galaxies to study. They might conclude the universe is static, eternal, and consists only of their galaxy surrounded by infinite empty space. Ironically, they would return to a view similar to what humans believed before the 20th century, but for completely different reasons. We live in a special epoch, a golden age when the universe is old enough to have formed structure but young enough that we can observe distant galaxies and the cosmic microwave background. Future observers will not have this privilege. The knowledge we gain now is time-sensitive, accessible only during a limited window in cosmic history. This lends urgency to our efforts. We should map the universe as completely as possible while we can. Every delay means some information is lost as distant objects recede further, becoming fainter and harder to observe. Every year we wait is a year fewer observations remain possible before objects cross the horizon. The KBC void reminds us of this urgency. It is a structure we can study now, characterize with current observations, understand within our lifetime. Future generations may have better instruments but a smaller universe to study. We should not waste the opportunity we have. Let us take a moment to reflect on what the KBC void teaches us about cosmology itself, about how we do science when studying the entire universe from a single location within it. This is worth pondering because it reveals both the power and limitations of our methods. Cosmology is uniquely challenging among sciences. In most fields, we can conduct controlled experiments, vary conditions systematically, repeat measurements many times. A chemist studying reactions can run the same experiment hundreds of times with slightly different temperatures or concentrations, building statistical understanding. A biologist studying organisms can examine many individuals from different populations, comparing and contrasting. But cosmology offers no such luxury. We have one universe observed from one location at one moment in cosmic time. We cannot rewind and watch events again. We cannot move to different vantage points light years away to compare perspectives. We cannot vary universal constants to see what happens. We are confined to Earth, peering outward through telescopes, trying to understand everything from this single, fixed perspective. This limitation makes cosmology more like archaeology or geology than laboratory physics. We are detectives examining evidence, reconstructing history from clues, building models to explain what we observe. We cannot experiment directly on the universe, but we can observe different parts at different distances, which means different times due to light's finite speed, building a picture of how things change and evolve. The cosmic microwave background is crucial because it provides a baby picture of the universe, showing conditions when structure was just beginning. By comparing that early state to the present, we trace 13 billion years of evolution. The early universe was smooth. The present is structured. Gravity transformed one into the other following laws we can calculate. This gives us confidence we understand the basic story. But here is the subtlety the KBC void exposes. All our observations are local in a cosmological sense. When we measure the Hubble constant using nearby supernovae, we sample our cosmic neighborhood, perhaps 1 billion light-years across. That sounds enormous, and it is by human standards. But cosmologically, it is local. The observable universe extends 46 billion light-years. Our local measurements sample only a small fraction of this volume. If our local neighborhood is typical, representative of the cosmic average, then local measurements reflect universal properties. This is what we assumed, consciously or unconsciously, when interpreting observations. We measured local expansion and called it the Hubble constant, implying it applies everywhere. We measured local structure and assumed it represents typical cosmic structure. But what if our neighborhood is not typical? What if we live somewhere unusual, in an atypically large void? Then our local measurements are biased, systematically different from cosmic averages. Not wrong, exactly, but not representative. They tell us about our location, but not about the universe as a whole. This is unsettling because it means we have been less careful than we should have been about accounting for local peculiarities. It is like measuring Earth's properties while assuming we sit at a random location, then discovering we are actually at the North Pole. Arctic temperatures are real temperatures, valid measurements, but they are not representative of global averages. Similarly, measurements made from within a large void are valid, but potentially biased. The KBC void forces us to think more carefully about selection effects, about what we can and cannot infer from observations made from our particular location. It makes us question assumptions we took for granted. This is uncomfortable but healthy. Science advances by questioning assumptions, by discovering that things we thought we understood are actually more subtle. In a sense, the void reminds us that we are still Copernicans in training. We have learned that Earth is not the center of the universe, that our location is not cosmically special in most ways. But we are still learning what this really means, still discovering the implications of observing from one random location rather than from some privileged cosmic viewpoint. The challenge going forward is to account for our location more carefully. This means better mapping of our local environment, understanding its properties in detail. It means carefully modeling how local structure affects observations. It means being humble about which measurements reflect local conditions versus universal properties. This is difficult work requiring patience and rigor. We cannot simply correct for the void's effect by applying some standard formula. The void's influence depends on its detailed three-dimensional structure, on where exactly we sit within it, on how other nearby structures contribute. Disentangling all these effects requires comprehensive data and sophisticated modeling. But it is possible in principle. With enough observations, enough computational power, enough theoretical understanding, we can account for our location and correct our measurements. We can map the void, model its effects, and extract the true cosmic parameters from our biased local measurements. This is the path forward, difficult but navigable. The void also teaches us about the importance of multiple independent probes. If we relied only on local measurements of the Hubble constant, we might never realize there was a problem. But we have the cosmic microwave background providing an independent measurement from completely different physics at completely different times. When two independent measurements disagree, we know something is wrong, either with the measurements or with our understanding. This principle applies broadly in cosmology. We should never trust a single measurement or single method. We need multiple independent probes that can cross-check each other. Gravitational lensing checks galaxy dynamics. Supernova observations check cosmic microwave background inferences. Large-scale structure observations check predictions from inflation. This web of cross-checks gives us confidence when different methods agree and alerts us to problems when they disagree. The Hubble tension is exactly such an alert. Two methods disagree, telling us something is wrong. Maybe it is systematic errors in one or both measurements. Maybe it is the KBC void affecting local measurements. Maybe it is new physics we have not considered. Whatever the answer, the disagreement is telling us something important, forcing us to look deeper, to question assumptions, to refine our understanding. This is science working as it should, not providing clean answers on demand, but revealing puzzles that require patient investigation. Not confirming what we already believe, but challenging us with observations that do not quite fit our models. The void is not breaking the universe. It is breaking our complacency, our assumption that we fully understand how to measure the universe from our particular location within it. What can we conclude about the KBC void? Let us synthesize what we have learned without retreating into comfortable certainties. Multiple independent analyses using different galaxy catalogs and statistical approaches consistently identify a large, underdense region in our cosmic vicinity. The evidence for this structure is robust, not dependent on any single measurement or technique. Its approximate size, approaching 1 billion light-years in radius, places it among the largest known voids in the observable universe. Whether it is the absolute largest remains uncertain given observational limitations at great distances, but it is certainly exceptional. Standard cosmology does not forbid such structures, but it predicts they should be rare. How rare depends on detailed calculations involving the full distribution of density fluctuations and their nonlinear evolution. Different studies arrive at different probability estimates, ranging from uncomfortably low but not impossible to genuinely problematic. This range reflects genuine scientific uncertainty rather than evasiveness. The calculations are difficult, involving complex physics and statistical subtleties we cannot fully resolve with current understanding. The void's potential role in the Hubble tension remains an active area of investigation. Simple estimates suggest a structure this large could bias local measurements by the required few percent. More sophisticated calculations accounting for three-dimensional structure and our uncertain position within it sometimes support this conclusion, sometimes find it insufficient. The question is not settled. Multiple factors may contribute to the tension, with the void being one element rather than the complete explanation. Questions about observer selection and our location's typicality resist definitive resolution. They involve not just empirical science, but interpretation, philosophy, and assumptions about probability that cosmology struggles to address rigorously with only one universe to observe. Reasonable scientists hold different views on these matters, and the debates will likely persist as more philosophical than empirical questions. What observations can resolve is the void's physical properties and its consistency with structure formation models. This requires international collaboration on a scale unprecedented in astronomy's history. Teams across continents coordinate observations, share data through standardized formats, develop common analysis pipelines, and publish results for community scrutiny. The major surveys are not single institution efforts, but collaborations involving hundreds of scientists from dozens of countries, pooling expertise and resources to tackle questions no single group could address alone. This collaborative structure has practical and philosophical implications. Practically, it accelerates progress by distributing work, cross-checking results, and combining complementary skills. Philosophically, it embodies science's ideals: open inquiry, transparent methods, results that survive independent verification. When multiple teams using different instruments and techniques reach similar conclusions about the void's properties, confidence grows not from authority, but from convergent evidence. What future observations can clarify is the void's detailed structure and its comparison to theoretical predictions. Upcoming surveys will measure millions of additional galaxy redshifts, mapping underdense regions more completely and accurately. They will identify other large voids across cosmic volumes, allowing statistical comparison. They will refine measurements of how our local expansion rate deviates from cosmic mean. They will test predictions about void formation under various cosmological scenarios. These observations will not resolve all questions. They cannot tell us whether our location is philosophically surprising or whether we are overthinking coincidence. But they can narrow uncertainties, distinguish models, and clarify whether the void challenges standard cosmology or merely represents its extreme tail. Perhaps the void's greatest contribution is pedagogical. It reminds us that cosmology is difficult precisely because we observe from within what we study. Measurements are inevitably local, even when they sample vast volumes. Local need not mean typical. Corrections for our particular circumstances are necessary, but not always straightforward. Humility about what we can infer from our single vantage point is appropriate. The void also exemplifies how science progresses through puzzles. Not every observation fits comfortably into existing frameworks. Some discomforts are resolved through better measurements or refined analysis. Others point toward genuine gaps in understanding. Distinguishing these cases requires patience, rigor, and willingness to follow evidence wherever it leads rather than forcing observations into preconceptions. Our cosmic address, an ordinary galaxy in an extraordinary neighborhood shapes everything we observe in ways both obvious and subtle. Recognizing this does not diminish our achievements in understanding the universe, but rather highlights their remarkable nature. That we can identify our location's peculiarities, calculate their effects, and work to correct for them demonstrates cosmology's sophistication and self-awareness. The universe reveals its nature grudgingly, through careful observation and patient analysis. Large structures like the KBC void emerge slowly from data, their implications debated and refined over years or decades. This is cosmology's reality, far from popular images of dramatic eureka moments, but closer to science's actual practice of incremental progress, punctuated occasionally by genuine surprises. Whether the void ultimately proves crucial for resolving the Hubble tension, or merely interesting as an exceptional structure, or perhaps less extreme than current estimates suggest, the work of characterizing it advances our knowledge. We map our local universe more completely. We test structure formation models more rigorously. We develop techniques for accounting for selection effects more carefully. These contributions have value independent of any single conclusion about the void's significance. The vastness of this emptiness surrounding us, if indeed it extends as far as measurements suggest, is humbling in its own right. Most cosmic volume is empty in this way, galaxy-poor regions occupying far more space than the bright filaments and clusters we photograph. We are reminded that the universe is mostly empty, with matter and light being rare exceptions rather than the cosmic norm. Our perspective from within a galaxy in a void may be unusual, but perhaps not as unusual as initial impressions suggest when we account for volume rather than galaxy counting. Time will refine our understanding. Observations will accumulate, theories will adapt or fall. What remains uncertain today may become clear within years or decades. Or perhaps some questions will persist, marking genuine limits of what we can determine from our particular cosmic circumstances. Either outcome represents progress, clarifying what we know, what we can know, and what remains beyond our current reach. This is the nature of science at the frontiers, where observation meets interpretation and certainty yields to careful probability. The KBC void represents more than just an astronomical curiosity or potential explanation for measurement discrepancies. It embodies a profound challenge about how we conduct science when we are embedded within what we study. Every cosmological observation is filtered through our location, our time, our particular cosmic circumstances. Recognizing these filters and correcting for them requires sophistication we are still developing. This challenge will only grow more acute in the far future. As dark energy drives accelerated expansion, distant structures will recede beyond our observable horizon. Future civilizations, if they arise, will inherit a smaller observable universe with less information available. They may lack evidence we currently possess, unable to discover truths about cosmic structure and expansion that seem obvious to us. Our era, when the observable universe spans 90-some billion light-years and contains billions of galaxies spanning a vast range of distances and epochs, may represent a narrow window of cosmic time when understanding cosmology is possible. This realization adds urgency to current efforts. The observations we make now, the surveys we conduct, the catalogues we compile, these are not merely incremental additions to knowledge, but potentially irreplaceable records of cosmic structure before it recedes forever beyond observation. Future cosmologists may look back at our data with envy, wishing they could see what we see while we still can. The void itself will persist far longer than human civilization, far longer than Earth's habitability, far longer than stars themselves. It is a permanent feature of our cosmic neighborhood, at least on timescales relevant to any conceivable intelligent observation. Long after we are gone, the underdense region will remain, its galaxies separated by vast distances, its space emptier than average, a gentle hollow in the cosmic web. But its significance lies not in its longevity, but in what it teaches us now. Every large structure discovered, every deviation from expectations detected, every measurement that challenges our models, these advance understanding not by confirming what we already believe, but by revealing where our beliefs need refinement. The void serves this function admirably, pushing us to think more carefully about structure formation, about measurement systematics, about our cosmic address and its implications. The questions it raises may not all be answerable. Some may remain perpetually uncertain, limited by fundamental constraints on what we can observe or calculate from our single vantage point. This is not failure, but honesty, acknowledging that science has boundaries while continually working to expand them. Understanding what we cannot know is itself a form of knowledge, perhaps as valuable as understanding what we can. Astronomers will continue mapping the void, measuring galaxy distributions, refining distance estimates, modeling gravitational effects. Theorists will continue calculating structure probabilities, simulating void formation, exploring parameter space. The community will continue debating interpretations, questioning assumptions, testing hypotheses. This is how progress happens, through sustained effort across many minds and many years, gradually narrowing uncertainties and clarifying understanding. Whether the void ultimately proves central to resolving cosmology's current puzzles or remains a fascinating outlier in the distribution of structure, the work is worthwhile. Science advances through accumulation of knowledge, through refinement of techniques, through development of conceptual frameworks that let us ask sharper questions. The void contributes to all of these, regardless of its final significance. And so we find ourselves here, in this particular place, at this particular time, blessed or cursed with consciousness that lets us ask where we are and what it means. The answer, a galaxy among thousands in a vast underdense region that may challenge our understanding of cosmology, is both humbling and extraordinary. Humbling because it reminds us how circumstantial our knowledge is, how much depends on where and when we happen to exist. Extraordinary because despite these limitations, we can recognize them, account for them, and continue pursuing understanding with sophistication that would have seemed impossible mere generations ago. The void awaits further study, patient and vast, indifferent to our efforts, yet central to them. Understanding it means understanding our place in the cosmos and the filters through which we see that cosmos. This is the work before us, difficult and fascinating, progressing slowly but advancing nevertheless, adding piece by piece to humanity's collective understanding of the universe we inhabit and the unusual neighborhood we call home. Living in the void raises questions about whether our location is typical or influenced by observer selection. These questions touch on deep issues in probability and cosmology's foundations. They may have no definitive answers, remaining matters of interpretation and philosophy as much as physics. Future observations will clarify the void's properties through multiple independent approaches. Better galaxy surveys will measure redshifts for millions of additional objects, mapping three-dimensional structure with unprecedented completeness. Improved measurements of galaxy peculiar velocities will reveal flow patterns around the void, testing whether matter streams outward as underdensity predicts. More sensitive observations of the cosmic microwave background will search for subtle temperature signatures associated with the void's integrated gravitational effect on traversing photons. Equally important is preserving these observations for future analysis. Modern astronomical surveys generate data volumes measured in petabytes, requiring sophisticated archiving systems and data formats designed for longevity. The observations we make today may be reanalyzed decades hence using techniques we have not yet invented, extracting information we cannot currently access. This requires careful curation, comprehensive metadata, and commitment to maintaining accessibility as storage technologies evolve. The astronomical community has learned from past losses where valuable data degraded on obsolete media or became unreadable when software evolved. Current best practices emphasize open data formats, thorough documentation, and distributed archiving. For the void specifically, this means future researchers will have access to the raw observations, not just published analyses, allowing them to test new hypotheses and apply improved methods as our understanding matures. But some questions may remain unanswered. We have only one universe observed from one location. We cannot run controlled experiments or sample alternate realities. We must work with what we have, extracting maximum information while acknowledging limits. The KBC void is not breaking the universe in the sense of violating physical laws. Voids exist. Underdense regions are expected. Even large voids are not impossible. But it may be breaking our complacency, our assumption that we fully understand cosmic structure and can measure the universe accurately from our location without worrying about local peculiarities. If nothing else, the void reminds us that cosmology is hard. We are trying to understand the entire universe using observations from a single vantage point. We assume we are typical, that our local measurements reflect cosmic averages. But if we are not typical, if we live somewhere unusual, our assumptions break down and our measurements become systematically biased. Correcting for such biases requires understanding our location within the cosmic web, mapping structure around us thoroughly, and carefully accounting for how local conditions affect observations. This is possible in principle but challenging in practice. It requires data, models, and computational resources that are only now becoming available. The story of the KBC void is still being written. Every year brings new observations, new analyses, new insights. The questions it raises will not be resolved quickly. Some may not be resolved at all within our lifetimes. But engaging with these questions, wrestling with the uncertainties, pushing observations and theory forward, this is how science progresses. We live inside something extraordinary, a vast cosmic emptiness spanning nearly 2 billion light-years. This is our neighborhood, our cosmic address. It shapes our view of the universe and potentially our measurements of its properties. Understanding it means understanding ourselves, where we are, how we fit into the larger cosmic structure. The universe is not uniformly filled with galaxies. It has texture, structure, pattern. It has dense regions and empty regions, filaments and clusters and voids. We happen to live in one of the empty regions, one of the largest such regions known. This is our cosmic circumstance, neither chosen nor changeable, simply a fact we must account for when studying the universe around us. Perhaps there is something fitting about this. We are small creatures on a small planet orbiting an ordinary star in an unremarkable galaxy in an unusually empty region of space. We are cosmically insignificant in most ways that matter. And yet, we can look outward, measure distances across billions of light years, map structure on cosmic scales, and ask whether our location is unusual. We can discover that we live in a void and then ask what that means. We can calculate probabilities, run simulations, debate interpretations. We can do science even when answering questions is difficult and uncertainties are large. The KBC void is a puzzle, a challenge, an opportunity. It tests our understanding and reveals gaps in our knowledge. It may eventually lead to new physics, or it may simply force us to be more careful about how we interpret observations from our particular location. Either outcome advances our understanding. We live in the void. The void may be breaking the universe, or it may be teaching us that the universe is more complex, more subtle, more surprising than our models capture. Either way, discovering this is remarkable. We are inside something extraordinary, looking out at a universe that contains mysteries we are only beginning to understand. The void surrounds us, shapes our view, challenges our theories. And we are here to witness it, to study it, to eventually, perhaps, understand it. This is science at its most human. We observe, we measure, we wonder. We construct theories and test them against reality. We disagree and debate, refine and revise. We live with uncertainty while pushing forward, seeking answers even when they are elusive. The KBC void is our cosmic home. Understanding it means understanding where we are in this vast universe, and perhaps why we can be here at all to ask such questions. That alone makes it worth studying, worth puzzling over, worth devoting our finest instruments and our best minds to characterizing as thoroughly as we can. We are inside the void, and from within this emptiness, we reach outward, seeking to understand everything that lies beyond.